Swayam Prabha. Digital India. Educated India.
Okay, in yesterday's class we solved a few problems in enclosure analysis. We started off with a one surface enclosure, namely we just took a plate which was having an emissivity of epsilon or epsilon 1, temperature was T or T1 and the outside was T infinity. We can consider it to be a black body at T infinity. We got the very familiar result, Q equal to epsilon sigma T to the power of 4 minus T infinity to the power of 4. Then we went on to solve the problem of a two zone or two surface enclosure where you have two parallel plates which are infinite in extent, so that F12 equal to 1. Then we wrote the radiosity relations. Then we founded J1 and J2. We founded Q equal to J1 minus G1 equal to J1 minus G2, and we got the familiar this parallel plate formula. This is a very important result which can be used to model heat transfer between two plates when the convection between them can be neglected. Even if the convection is there, you can add the convection to the radiation, and this addition is possible if the temperatures are known. If the temperatures are not known, you have to exploit the coupling. That will become what is called a conjugate heat transfer problem. Okay. Now even in this case, in yesterday's class we saw that when epsilon 2 equal to 1 and T2 equal to T infinity, it reduces to the simple case of a one surface enclosure. So it is all these results are consistent with common sense. They are also consistent with the way we understood. So this is called an internal consistency check. Alright. Now if you have two parallel plates, okay, even though you do not have convection between them, if the temperature difference between these two plates is sufficiently large, then high radiation heat transfer between them is inevitable. But many times we want to avoid this radiation heat transfer between them. Just because you have put vacuum, it does not mean that you have solved the problem. Okay. If both the surfaces have good emissivity and they are at a good temperature, and rather you have a good temperature difference, then the radiation heat transfer will not be insignificant. Therefore the challenge is now to come up with some method by which you reduce the radiation heat transfer between these surfaces. Therefore you can put some thin film which has got an emissivity equal to epsilon 3 or epsilon shield, and we try to find out what will be the radiation heat transfer when such a shield is inserted between two plates. Suppose we derive the formula for the heat transfer, radiation heat transfer with one extra shield, then by induction we can find out what will be the radiation heat transfer if you have 2 shields, 3 shields and n shield, and then we will solve a numerical example, so just so that you get an idea of so that it reinforces the concepts you have learnt, right. So we will go to the problem of radiation shield. So consider two vertical infinitely deep, infinitely long parallel plates which are at temperatures at temperatures T1 and T2 respectively, with hemispherical spectral emissivities epsilon 1 and epsilon 2. The intervening space is evacuated, that means there is vacuum in between. Okay. In the absence of any shield or in the absence of any medium in between, or in the presence of a radiatively transparent medium, you have already derived the radiation heat transfer between the two surfaces. Now I insert a shield. Now insert a radiation shield. Let the radiation shield have a known emissivity of epsilon 3 on both the sides. I have to be very specific in saying that both sides have the same emissivity, because emissivity is just a surface property. I can have different coatings on two sides, I can have different emissivity, but the whole shield may be at one temperature, but the two sides may be at different emissivity. Okay, we are still talking about an opaque, we are not talking about a transparent sheet or something. Okay. Now let it come to a let its temperature be T3. Let its temperature be T3. Now steady state prevails in the system. steady state prevails in the system. So the heat transfer, radiation heat transfer is taking place like this. So is the configuration clear? Now the challenge is to come up with, the challenge is to now come up with a mathematical expression for Q with the shield. Okay. Now Q13 can be written as, from the parallel plate formula, Q13 can be written as sigma T1 power 4 nothing great. So okay, but I may not know T3 at this point in time. T3 is the equilibrium temperature of the shield. Okay, right, we will talk about it little later. By the same token, okay, what can you say about Q13 and Q32? Under steady state, Q13 must be equal to Q32. It is also equal to Q12 with shield. Is it correct? It's eventually the heat which is going from the left to the right. So we can say it as, we can qualify it as saying that it's Q12 with shield. Q12 without shield is this. Correct? Now okay, Q12 comma shield, so that you do not get confused. Therefore, why?
From 3 the radiation can go to 1 and 2. No, but
3 has 2 surfaces. 3 itself has 2 surfaces, isn't it?
so that formula was from the assumption that 3 factor is 1.
It is. Come again. Somebody else may have the same doubt, but they are shy of. Come again.
3 2.
Yeah, 3 to 2. There is nothing else. It cannot go on the back side because they are surfaces. It may be a shield, but radiation is a surface property. The front side may behave differently from the back side. They have no connection. The view factor on the front side and back side are not correlated at all. Is that clear? That's a good point. Okay. I am not very happy with this formula. Which formula? This one. Because normally in engineering applications we are keeping 2 plates. It is easy for us to measure the temperature of the 2 plates. If I put some shield, why unnecessarily take the trouble of putting a thermocouple and measuring the temperature? So for all practical purposes we will treat the T3 as unknown. So the T3 has to be eliminated. I do not like T3, it is useless for me. With this expression I cannot calculate. Is the point clear? Okay. Now you can do your mathematical manipulation and eliminate T3 and all that, but I have again a very cheeky way of doing it. So I will say if half is equal to 2/4, this is also equal to the dividend component rule. Therefore, is also equal to the sum of the numerator and denominator separately, correct? Yeah, you can get the same result with lot of labor if you were not to use the dividend component rule. Still it is possible. You can substitute for T3 from here, you will cross multiply, you can do all that. Okay. Now you can assign numbers to this if you want. Therefore, is this clear? Yes. So what I did was I added the numerator and denominator separately, and then say I am declaring that it is the same Q12 shield. Fortunately for us, there is a minus T3 to the power of 4, here there is a plus T3, they are getting cancelled. Okay, Q is that fine? If all the epsilons are equal, is it okay, Shrikant? Arjun, checking? Check it, check. Now, if all the epsilons are the same, what will be Q12 no shield? Yeah, if all the epsilons are the same, then Q12 no shield will be sigma T1 the 4 minus T2 the 4 divided by 2 by epsilon minus 1. Therefore, Q12 shield divided by Q or Q12 Q12 shield is equal to Q12 no shield divided by n plus 1, where n is the number of shields. Okay, is that clear? So we will write it out formally. Therefore, therefore, it is possible to insulate some surface radiatively by employing n number of shields, right. So, just because you have vacuum, it does not mean that you have already insulated. If you have vacuum, you remove the convection, okay, and there is no conduction because nothing is, because there is no medium, but radiation will be there. If you have evacuated and you also have n shields, you get what is called a radiation super insulation, okay. This is the concept of a super insulation, okay. You can make some thin sheets and insert. The position of the sheet does not matter at all, okay, so long as it is infinite in extent, otherwise the view factors will come into play and all that, okay. Let us solve a numerical example. While the heat transfer rate is straightforward, suppose for some reason I want to know whether this radiation shield I have introduced can withstand some particular temperature, it is imperative on my part to evaluate the T3. The T3 has to be evaluated as a post process quantity and see whether that T3 is okay for this material. Without the T3 we got this result, okay. So, now as a post processing step you will have to evaluate the T3. Let us solve a problem in which you determine both the Q and the T3, okay. Problem number 32, very good. Determine the steady state temperatures, determine the steady state temperatures of two radiation shields, determine the steady state temperatures of two radiation shields placed in the evacuated space, determine the steady state temperatures of two radiation shields placed in the evacuated space between two infinite plates determine the steady state temperatures of the two radiation shields placed in the evacuated space between two infinite plates at temperatures of 600 and 300 Kelvin respectively, between two infinite plates at temperatures of 600 and 300 Kelvin respectively. All the surfaces are grey and diffuse, all the surfaces are grey and diffuse with emissivities of 0.85, all the surfaces are grey and diffuse with emissivities of 0.85, okay. Please start solving. The figure is not required, nevertheless I will draw the figure for the sake of completeness. Okay, so there are two plates, 1 and 2. There is no need to call the emissivities as epsilon 1, epsilon 2, epsilon 3, epsilon 4, all are equal to 0.85 epsilon is enough, okay. T2 equal to 300 Kelvin. Now I have put two shields. How many surfaces are there in this problem totally? 6 surfaces are there. There are 2 surfaces for the 2 shields, which makes them 4 surfaces, and 1 surface each. We do not care about the left side of 1 and the right side of 2. We do not care about these 2, but we do care about the left side and right side of the intermediate fellows. Okay. So point T3 equal to not known, T4 equal to not known. So simply write the no shield formula divided by n plus 1, n equal to 2, therefore n plus 1 is 3, you will get the Q with 2 shields. Then this Q with 2 shields you locally apply between 1 and 3 to get the temperature of 3, you locally apply between 3 and 4 to get the temperature 4. You have to do it systematically, this will take somewhere between 10 to 15 minutes, it is pretty straightforward. Okay. Okay. First we will write the Q12 no shield. Five thousand 91.9. What are the units? Watts per meter square area. Okay. This is the first step. Okay. Now we have to do Q12 2 shields. Five thousand 91.9 divided by 3. All right. Correct. Five 46.3. Okay. If all the emissivities are not the same, more labor is involved, it will become more painful, that is all, but most of the relations will hold good. Everybody got this 546.3? So, the interesting thing is if both the surfaces are black, and you have a shield, okay, the equilibrium temperature T3 will be T1 to the power of 4 plus T2 to the power of 4 divided by 2 whole to the power of 0.25. Okay, I do not know, is it, it is not harmonic mean, what mean is it, I do not know. You take the fourth power, take the average and then take the fourth root. Tell me.
Fourth power to the arithmetic.
So it is that is the way it works. So you will get an approximate idea of, okay, T1 to the power of 4 plus T2 to the power of 4 divided by 2 whole to the power of 0.5. Do not take it as the formula, only if the two are black and other things. This is asymptotic case. Always when you do some engineering analysis, you must look at the asymptotic case. What happens? What happens if both are black? What happens if emissivity is 0? What happens if T2 is equal to T infinity? Those somewhere you must get an answer which is consistent with your common sense. Then you know, okay, this must be right. Okay. Now we will do the last part. The other way of checking is T3 and T4 must be between T1 and T2. Okay, otherwise you are in trouble. There is no heat generation in the problem. Heat is flowing from left to right. So from left to right the temperatures have to continuously decrease. Okay, so these are what are called common sense checks. Okay, now T4. For 69.4. So now we have got all the answers. What will be the heat flux without the shield? What is the heat flux with two shields? What are the intermediate temperatures? We have answered all the questions. Okay. Now let us solve a problem involving a two zone enclosure. It's slightly more involved. Yes, Srikanth.
Anywhere actually, we just use the fact that they are equal. For finding out the temperatures, we didn't use 0.85, it gets cancelled. So
where?
Regardless of
we don't need the
as long as they are equal, you still get
As long as they are equal, yes. Otherwise you have to take that. Yeah, because what you are saying is for 1697.1 itself you are, what he is saying for 1697.3 itself you are taking 2 by epsilon minus 1. So epsilon will, so it is some sort of an equilibrium temperature which is mostly determined by the other two temperatures, that is all.
So even if the emissivity is something else, finally it will remain the temperature.
Yeah, but I am not sure what you are saying. I agree with what you are saying, but if epsilon 3, if epsilon 3 1 is different from epsilon 3 2 1, epsilon 4 3 is different from epsilon 4 2, then we are in trouble. And then if each of these is different from epsilon 1 and epsilon 2, if all the, so what he is saying is he is qualifying whatever I told a little earlier further. I told you they have to be black, but he says so long as all are having equal emissivity, whatever I told, T1 to the power of 4 plus T2 to the power of 4 divided by 2 whole to the power of 0.25 holds, correct. That you can call it as TEQ. What is EQ? Equilibrium temperature. Okay. In fact, a re-radiating surface will also behave like this. Are the two shields re-radiating surfaces? Yes. Whatever heat they receive from the left side, they give it to the right side. So the Q net from that surface is 0, correct. Q net is whatever is going from right minus whatever is going from left, whatever is coming from the left is positive, whatever is going from the right is negative, so they cancel out, correct. So in fact too the radiation shields are radiating surfaces. Yeah, but if you consider them as one body, okay, because they have only one temperature. Because they are a re-radiating surface, the temperature or radiosity must be independent of their emissivity. That is what we derived in yesterday's class, right. See, if you work out, that is why you see that if you work out problems, you can understand the subject, you can appreciate the subject better, okay. So the common complaint that people are using software is not true, very correct. Suppose you continuously keep on using Fluent, it is possible that your fluid mechanics knowledge will increase because you will learn how to interpret it, but you repeatedly use Fluent for a long time, then hopefully your knowledge of fluid dynamics also improves. Okay, now we look at a very interesting problem. Okay, where okay. I will explain the configuration to you, okay. I have a flat bottomed hole, a hole has been bored into a plate, the depth of the hole is 24 millimeter and the diameter of the hole is 6 millimeters. It is evacuated or it is filled with air which is radiatively non-participating. The temperature of the surface 1, that is which includes the bottom as well as the lateral surface area of the bored hole, is basically 1000 Kelvin, okay, and this has an emissivity of 0.6, let us say. Okay, this has an emissivity of 0.6. It is opening this hole, this bored hole is opening to the surroundings at 300 Kelvin. Now we can treat it as a two zone enclosure problem, that is this whole thing is surface 1, that is 1, 2, 3, that is this lateral area, and the bottom is surface 1 which is having an emissivity of 0.6, it is at 1000 Kelvin. Surroundings are at 300 Kelvin, you treat the surroundings to be a black body at 300 Kelvin, two zone enclosure you can solve and get the resultant heat transfer from 1 to 2. But the beauty of this problem is, suppose this hole were not there, and you have this surface alone, okay, you just have the surface 2, right? That is you have something like this. This is basically a circle with a radius of 6 millimeters. But now I say this circle of 6 millimeters radius is a surface which is a black body. Okay. Now this is at 1000 Kelvin, it is also losing heat to the surroundings at 300 Kelvin. This will dissipate a certain quantity of heat to the surroundings. I want to see compared to this how much this will dissipate. the ratio of these two is called the effective emissivity. Why is it so? Because we saw the whole RAM, if I make it like this, there is so much of internal reflection that the radiation coming out of this will be equivalent to the radiation coming out from a black body at this temperature. Therefore, as the depth of the hole keeps increasing further and further, its effective emissivity will approach 1. So why so much pain and difficulty we want to take? Suppose we don't get a surface which is having a good emissivity, it is possible for us to bore holes in a few places and increase or augment the heat transfer passively without using any pumping power. Is the concept clear? Now please take down the problem. A flat bottomed hole 6 millimeters in diameter, a flat bottomed hole 6 millimeters in diameter is bored, B-O-R-E-D. A flat bottomed hole 6 millimeters in diameter is bored to a depth of 24 millimeter. In a gray diffuse material. In all the problems this will come, gray diffuse. In a gray diffuse material having an emissivity of 0.6. In a gray diffuse material having an emissivity of 0.6 and a uniform temperature of 1000 Kelvin. The surroundings are at 300 Kelvin. Gray diffuse material, emissivity 0.6, temperature 1000 Kelvin, full stop. Surroundings are at a temperature of 300 Kelvin, full stop. A. Determine the net radiant heat transfer. A. Determine the net radiant heat transfer leaving the opening of the cavity. Determine the net radiant heat transfer leaving the opening of the cavity. B. The effective emissivity epsilon effect, epsilon EFF. The effective emissivity epsilon EFF of a cavity is defined as, I am giving you the definition, the effective emissivity of a cavity is defined as the ratio of the radiant heat transfer from the cavity that is what you calculated in part A, correct? Okay, the effective emissivity is defined as the ratio of the radiant heat transfer from the cavity to that from a black body having the area of the cavity opening, to that from a black body, what Mudit, lost track or ratio of radiant heat transfer from the cavity to that from a black body having the area of the cavity opening and the temperature of the inner surfaces of the cavity, So, the concept I have already explained, what I have given is a mathematical definition, full stop. Calculate epsilon effective for this cavity, okay, calculate epsilon effective for this cavity. Part C, if the depth of the cavity increases, will epsilon effective increase? If the depth of the cavity increases, will epsilon effective increase? If so, what is the asymptotic limit? So, a lot of fundas are inbuilt into this problem. The first part of the problem is simple two zone enclosure. Okay. Now please retain up to 3 or 4 decimal places, is very tricky, right. Okay. Now let us start solving. So what is the first step in an enclosure problem? View factors, very good. So, okay, solution. F11, F11 I do not know, F21 1, F22 so A1 so R equal to 3 millimeters, H equal to 24, correct. Pulara, is it okay? Fine. Please tell me A1 and A2. .8 into 10 to the power of 4.8 into 10 to the minus 4. Okay. Correct. Samajit, is it okay? Calculated? Let's check A2 first. Tell me if I made a mistake. It's 2 pi r square, right? Fine? Okay. Okay. So, F12 0.058, very good. Okay. Sorry, F11, correct? That is F11, okay. Right? Now, we write the radiosity relations J1 what is J2? J2 is a black body at T infinity, sigma T2 to the sigma 459.3, what is the value? 5.67 10 to the minus 8 into 300 to the power 4, power 4. .3, huh? So certain values you should remember. For 1000 Kelvin you will get 56,700 watts per meter square. That is clear, 5.67 10 to the power of minus 8, right. into 10 to the power of 12. Okay. Now what is now why unnecessarily, we can use this, right? Fine. Let us get J1 now. Yeah, please do the algebra. So you will have 0.4 into 0.942, so huh? 56,000, 55,000, no, we have to be careful, 54,000, 54,006, 0.5, yeah, okay, all of you should get this radiosity. So Q1 3,000, 3,000, this is only the flux, okay. This is the heat transfer rate, how much is that, into 4.8 into 10 to the minus 5, minus 4, it's some 1.5 watts, how much is it, okay, 1.51 watts. So this is the solution to the part A of the problem, okay, net radiation heat transfer. I hope Einstein it's clear, okay, but we will have to revise this, okay. Now as far as part B is concerned, what will be Q1 for the black body, that is the opening, there is a 6 mm dia surface which is having a temperature of 1000 Kelvin, which is radiating to outside at 300 Kelvin, correct. So this is how much is this, okay, 1.59 watts, okay. A2 is the area of the opening, pi d square by 4, where d is 6 millimeter, Stefan Boltzmann constant, 1000 Kelvin minus 300. Please be careful to multiply only the area A2 because that is from the definition given in the part B of the question. Now epsilon effective equal to how much is it? Very significant result. I have the surface, please look at me for a minute. I have the surface. If I take a 6 millimeter hole, the area is pi d square by 4, it can emit only pi d square by 4 into sigma into 0.6 into 5.67 into 10 to the power of minus 8. Okay, the maximum will be 1 into sigma into 8 into 5.67 10 to the power of minus 8. Now, if I have a gray diffuse material with an emissivity of 0.6, which has a, for example, for a hole of 6 millimeters diameter, there is only this much, there is a finite amount of heat transfer it can emit, it can lose to the surrounding. Suppose I bore a hole, then I can get a heat transfer rate of 1.51 watts. Okay. Suppose I just leave an area at the top like this. If it is a black body, the heat transfer rate is 1.59. If it is a body with emissivity of 0.6, the heat transfer is only 1 watt. Are you getting the point? Therefore, by boring a hole from 1 watt, we are able to take it up to 1.51. So, if I keep on increasing the depth further, it is possible for me to reach the asymptotic limit of 1.59, but never will I be able to exceed sigma t to the power of 4 minus T infinity to the power of 4 into pi d square by 4. Okay. All this increase of the effective area because of the increase in the depth is only helping me overcome my deficiency of having a poor emitter of 0.6, because it is very difficult to get a black body, and suppose from 0.6 to 0.9 I have to put some costly coatings or something. If the material is thick enough, I will put a hole in several places and passively increase the heat transfer rate. This is a technique adopted. Okay, fine. For fluid mechanics also, in golf balls they put dimples and all that to increase heat transfer rate, also to, and somebody is doing a BTech project on golf balls, I remember. Okay,